in our definition of sample space was just a set. It had no structure. But if you look at the random experiments which you had seen before, which you're going to see in the future, most of the time there is some kind of a numerical value. There is a number we are interested in. For example, if you toss a coin multiple times, let's say we are interested in the number of heads. If we go to a casino and place our bets randomly, we might be interested in amount of money earned through these bets. The outcome could be win or loss, but there is a number attached to these outcomes, and that's what we are interested in. If we want to figure out, okay, one of you or how many people attend my class regularly, and there is some probability that some people attend, some probability some people attend, but then an interesting number could be the number of days a particular student misses the class. These are just some examples, and you will see that most of the time we are asking those kind of questions. So these numbers are really interesting. These numbers are assigned to set of possible outcomes. This gives us an idea of how to define random variable. Let me give a formal definition. It's not difficult. It's simply a function from sample space to real numbers. Let's start with this definition. I will tell you that in literature there might be some modifications. We will worry about that, but for this course, let's assume that this is the definition. That basically means if you have set of outcomes omega 1, omega 2, omega n, you assign a numerical value to each of these. xw1, xw2, xw1. In case, suppose if I toss a coin twice, what will be my sample space?
Head, tail, and tail.
And if I say that my random variable should count the number of heads, then for this omega, what is the x omega? What is x of ht?
1.
1, right? X of th is also 1. X of tt?
0.
0, and x of hh 2. Right? So this is the simple function I am talking about. I am just giving a mathematical definition to it, but it should be very intuitive of why we would need such a function, because we want to assign value, some kind of you can think of a monetary benefit, some kind of a number of days, some number to each of the possible outcomes. And then xw is the value of the random variable on the element of the sample space. X omega is the value of random variable on the element. Any questions about this definition? What does it mean that x is a function? That means xw has a
unique value.
Unique. Exactly. I'm not saying that the function is 1-to-1. It can happen that xw1 is equal to xw, like it happened here. Okay, I'm just saying it's a function from omega to a number. Let me clarify that this is not the definition in many of the probability books. These, in a very general context, these will actually be called real valued random. Okay, in general, your range need not be real numbers. It could be any set of interest. It could be any group, any field, something with a much more structure than just coding. Something where you can apply some operations, you can add, you can subtract, and things like that. But for this course, I would assume 99% of the time, we will only worry about random variables whose range is a real number. That's why whenever I say random variable, you should think of real value random. Random variables whose values is a number, is a real number. Okay, is this distinction clear? In general, the range need not be reals. It could be something, some other set also, but most of the time we will be interested in the random variables which take a real value. Okay, this is what we are going to study in this course. Okay, and it could happen that your range is discrete, even though you're allowed to have all real numbers, your x only takes a few values. For example, here you know that x could only take values from 0, 1, and in that case, it will be called a discrete range. Okay, when I say I should not say range in two ways. One is what are the possible outcomes of x out of real numbers. Uh, those are what I'm calling a range. So even though x is allowed to have any real number, for a particular instance of x, it might only take certain value. For example, whenever I'm counting number of heads, it has to be an integer. Things like that. So when the range is discrete, then it is called a discrete random variable. Just for your knowledge, not that important. What you have to remember in mind, what is a random variable? Can someone tell me what is a random variable?
A function from sample space to real number.
Very good. And now if I want to ask you a question, why do we want numbers instead of a set? Why did we create this new definition of random variables? Do we get some advantage when we say we have numbers instead of just a set omega? And I'm probably pointing you towards what you have learned in abstract algebra. Yes, so Aditya is correct. It's not easier to operate on numbers. You can only operate on something which has structure, right? Remember, what were groups? Groups were a set with an operation. Once your sample space, you have moved your sample space to numbers, you can add these numbers. You can subtract these numbers. You can multiply. You can do all these operations because you are now in the realm of fields. You have a nice set of sample space. In some sense, when you are writing x, you have changed your sample space. Instead of omega, now your sample space is r. You view your outcomes as numbers instead of just red, blue, green, or things like that. Right? For example, if you had a bucket and it had red, blue, green balls, you might not want to add red with green. There is no meaning of red plus green. But if I assign red 1, blue 2, and green 3, then suddenly you can add these numbers. And is it interesting? I don't know, but you can start adding, subtracting the outcomes of your random experiment. And you will see now that we can talk about expected value and all those things, because now we are dealing with numbers instead of just a plain set omega. Remember, these numbers are not probabilities. We will assign probabilities to these numbers, but these numbers themselves are not probabilities, right? And I guess once we work with it, we will get more and more clear. So let's talk about it. As soon as you define a random variable x, it gives rise to a natural event. What is that event? It's an event. An event is a subset of sample space, so it's an event containing all the outcomes which give me value x. For example, you remember when x, it counts the number of heads, and omega was th, ht, tt, and hh. What is the event x is equal to 1? What elements will be there?
For head, tail, and tail head.
Tail, head, and ht and th. Right. So we need not have a one-to-one mapping from our sample space to real numbers, but your x is equal to x. These events will partition your sample space. Right. Previously, we were interested in this 4 outcomes, and if you only care about number of heads, then you can just say that these are my all possible choices. This is my new sample space in some sense, right? And then I can talk about what is the probability of x is equal to 0, what is the probability of x is equal to 1, x is equal to 2. This is called the probability mass function of the random variable. And what do you think it should be? What should be the formula for probability mass function? I can sometimes write it as probability of x is equal to x. Sometimes I will just denote it by probability subscript capital X, small x. What should it be in terms of probability of omegas, right?
Maybe probability of W1 plus W2 means
Sorry?
that W that satisfies this XW equal to X. We can add their probability.
Exactly. This seems very natural. Right? This is how we can define the probability mass function of our random variable. If all the 4 outcomes in our example were equally likely, probability that x is equal to 0 is equal to
1 by 4.
yes, x is equal to 1,
Half.
and similarly probability of x is equal to 2 is 1 by 4. This is how you can define the probability mass function. Are there any questions?
So for the case of tail head and head tail, what would be omega?
So these are omega 1, omega 2, omega 3, right?
Yes, okay. These are different.
Yes, these are 4. I had 4 elements in my sample space, but if I was only interested in number of heads, then in some sense my random variable moves to a new sample space which has only 3 elements.
Okay, so but one question here, when you have written the definition for capital X equal to small x, by implies an event containing omega, but it would be a collection of all the events, right? For which x of omega is equals to small x.
Okay, so let me just say, does that clarify the confusion?
Yeah, yes, sir.
Thank you. Yeah, that's it. So it should be an event which contains all the omegas such that xw is equal to x. Okay, mathematically all w's such that xw is equal to x. And now we will take lots of examples and compute their probability mass function. That will make things clear. Okay, if we toss a coin 10 times, what is the size of the sample space?
2 to the power 10.
2 to the power 10, right? And every, let's say, every element is equally likely to start with. Okay, and then if we want to count number of heads, we want to compute the probability mass function of this. Okay, let's make it interesting. Let's say the probability of head is P. Okay, so it's a biased coin. I'm telling you the bias is P. The probability that I get a head is P and I get a tail is 1 minus P. Can I say that every element in my sample space has equal probability?
No, sir.
No, right? For example, all heads will have different probability than all tails if P is not half. So what is the probability of a random string of length 10, h, t, something h?
P to the power number of heads into 1 minus P to the power number of heads.
Is there anyone for whom this is not clear? Okay, this is clear now, right? So then what is the probability that x is equal to k? And what will these, what are the possible k's for this random variable?
Possible cases are 0 to 10.
Okay, good.
And probability would be number of strings for which heads can be a number heads can be equal to k.
What is that?
Into
What is that?
that would be 10 ck.
Very good. 10 choose k. Then
10 choose k into p ki power k into 1 minus p ki power 10 minus k.
Very good. Right. So this is the probability mass function for our random variable. Any question about this? This was simple, right? Let's take a slightly different example, probably a more complicated example than the one. If I suppose in a class of students, I start asking birthdays one by one. And once, if the birthday matches, I stop. So this is a random experiment. This will depend on, every person's birthday could be 1 out of 365 with equal probability. I keep asking it, I stop once I find the match. And now, what is the probability, what is the number of students queried? I want to figure that random variable x, right? So what are the possible values of k for x?
Excuse me, sir.
Yes.
Zero.
Sorry, there was a question.
Sir, this stop if the birthday matches, that means that if one person says the birthday and in the previous set of person the same birthday was there, then we stop, or if the
Exactly.
consecutive birthday.
No, it need not be consecutive.
Okay.
If the birthday matches with any of the birthdays we have seen till now.
Okay. Thank you, sir.
And so what are the possibilities for k?
2 to 367.
0, 2 to 360.
367.
Okay, so assume we have 365 days. Okay, we will assume that it's not a leap year. Then 366 is fine, right? And then what is the probability that x is equal to k?
We have it will be 1 upon 365 into 1 upon 364 into 1 upon 363 till 1 upon 365 minus k minus 366 minus k.
Okay, and why is that the case?
For each of the case, sir, it is a bit incorrect, I guess.
Okay.
For the last term, it would be for except for the last term, for each of the time we have to choose a day which is not already been taken. So for first case we will take we can take any of the day, so probability would be 1. Then for second case we can take a day which is not taken, so we have to exclude the day which is already taken, so it would be 1 upon 364. That was a mistake.
Okay, so let me just ask people who think that this formula is correct, please raise your hand. And if you don't think it is correct, then you should let me know what is the correct formula. So everyone thinks that this formula is incorrect. Then give me an alternate formula, right? What is the correct formula then? Do I see? So this is not a. This is something which you would have done in your high school, right? So again, okay, there are answers in the chat. Okay, one of the answer is. So this is a different way of looking at it. You choose k minus 1 birthdays, right? 365 choose k minus 1. They can come in any order. And then the first birthday has to be what you have chosen. That is 1 by 365. Second birthday also 1 by 365. So on. And then the last birthday should match with one of the k minus 1. So that is k minus 1 by 365. Okay. And this is the correct answer. Okay. So this will be 365 choose k minus 1, k minus 1 factorial, k minus 1 by 365 to the power k. This is the probability that x is equal to k. Okay. Okay. Let's go to one more example. You have 150 defective balls out of 1,000. So there is a set of 1,000 balls, 150 of them are defective. If we pick 50 balls and inspect, let's say x denotes the number of defective balls. So what values can x take?
Uh, 0 to 1, 0 to 50.
0 to 50, right? And what is the probability that x is equal to k? What are the total number of possibilities? I'm choosing 150 balls out of 1,000, right?
Thousand 350.
1,150, right? Okay. And then what are the favorable cases?
150 CK into 850 50 minus K.
50. Okay. So this is the probability. So this is these examples are simple. I think all of these are the kind of things which you have calculated before. We are just putting them in this new frame, in the new I shouldn't say new framework, in this idea of that. And you will see why random variables are important throughout this course, because again we are going to add them, subtract them, multiply them, do many of the operations, right? These were all examples of discrete random variables. You saw that the possible values were all discrete. There are obviously continuous random variables. We will talk about them, I think, in after 2 or 3 lectures. But there are continuous random variables. Okay, for today, we will stick to discrete random variables.
Sir, it should be 15, like in the denominator.
Where?
1000 say 50. Like we are choosing.
Oh, sorry. Yeah, you are right. It's 1,000 choose 50. Right? We are choosing 50 balls out of 1,000, and then k balls out of 150 come up, and 50 minus k out of 850 come up. This is the Now, given a sample space, how many random variables can be there on one sample space?
Like, sir, can you repeat the question?
Okay, given a sample space, how many random variables can be possibly be there on that sample space?
So like, it is a function, so like, it
Infinite,
can,
right?
Yeah.
It could be, there are many possibilities, but surprisingly, some people get confused and they think that there is a unique random variable for a random experiment. That's definitely not true. For example, when we are tossing a coin, we can ask number of tails, number of heads, number of head and tails and things like that, right? So definitely there is no unique random variable for a random experiment. In particular, if x is a random variable, then any function of x from R to R is also a random. Okay, so for example, 2x, if x is a random variable, 2x is a random variable, x square is a random variable, x cube is a random variable, etc., etc. Right? And then we can actually easily calculate the probability mass function of the new random variable. So let's define y is equal to gx. Okay, y is a random variable, x is a random variable. By the way, let me just clarify, this notation will be used here. When I write x is equal to x, what is on the left hand side? This is a
This is a function, like
this is a function or a random variable, right? X I'm noting by random variable, and this small x is a
value.
yes,
It is real number.
it's a value from R. It's a real number, right? So this notation should be clear that there are two things happening here. There is small x is just a simple variable for a number in R. It's a capital X is a random variable, and I will try to follow this notation. Capital letters will denote random variables. Small letters will denote the value taken by random. And then now the probability that random variable y takes the value small y is this probability. This is just how we define it. And then y is equal to y means g of capital X is equal. Right? And then we easily get the probability distribution function of the new random variable capital Y. Okay, we will just sum up over all possibilities such that g of small x is equal to small. This should be very intuitive. This is the formal notation, and let's make it work. Let's say our old friend x is the number of heads in 10 coin tosses. This was the probability distribution function which we got. Now, if y is equal to x square, what is the probability that y is equal to? Right? So first, there are two cases. What are the possible values of k for y?
Any square number from 0 to 100.
Right. Otherwise, the probability is
0.
And now, what is the probability that y is equal to k?
X equal to root k.
Right. So this is going to be p to the square root k, 1 minus p, 10 minus square root k, 10 choose, sorry. Square. Right. Again, I am just formulating them as a mathematical statement, but these things should be easy. Most of the time, you have a nice one-to-one function and you can just substitute the value of k as a function. So y is equal to x square, we substituted square root k and we got the probability of y. You have to be careful about what case are defined, and etc. In our CS courses, we won't get many difficult examples of this. In mathematics, they will do a lot of boundaries and things like that. For us, we just remember this is what it means for the probability mass function of y is equal to g of x. Okay, and you have gotten the idea of how to calculate it. We won't do much practice with that. For now. Is that okay? Questions about this probability mass function? Okay, if that is the case, then let's take another example. Why should we only worry about just one random variable, function of just one random variable? We said that we have two random variables. We can have multiple random variables on same sample space. Let's take their addition. If x is a function from omega to r, y is a function from omega to r, x plus y is also a function from omega to r. Right? Clearly that is true, and then let's take this as a random variable and try to find out its probability mass function, its PMF. So it should be probability that x plus y is equal. And like before, we want to sum up over all possible choices of x comma y such that x plus y is equal to, and this comma is just a shorthand for writing and. This probability is that x is equal to small x and y is equal to small y. But now the question is, I have the individual probability distributions of capital X and capital Y. Right? I have the probability mass functions of capital X and capital Y. What is this quantity?
Intersection for x equal to x and y equal to y.
What do you mean by intersection? Can you write it in terms of P of what? I have P of x is equal to x. I have P of y is equal to y. Let's take an example. Suppose I roll a dice twice. X is the number shown in the first roll. Y is the number shown on second. In that case, what will be this probability?
Multiplication of p of x equal to x into p of y equal to y.
Okay, so raise your hand if you think that this is the correct value for this p of x is equal to x. Okay, I see none of the hand raised. Then what is the correct answer? Yes, one person. So everyone else, what is the correct answer? If this is not the correct answer. Any opinions? Okay.
These are,
Okay, go ahead.
first one, x is for first dice and y is for value on second dice, right?
Mm-hmm. So for that case, this probability is correct. But in general, how should I write it? Should I just write it like this?
No,
What
not
if,
in general.
not in general, right?
In that case.
Right. So let's see what is the problem. In this case, we saw that this was y is equal to y. But if I take the case when capital X is equal to capital Y, right? I define the random variable y to be equal to x. Or let's say, if you want to be slightly more fancy, 2 times x is equal to y. Then what is the probability that x is equal to small x and y is equal to small y? These are all intuitive, right? So yeah.
So maybe like both of the event can't take simultaneously. Like
Yeah.
because
So if
yeah.
y is not equal to 2 times x, then the probability is
So probability is like
Zero.
0.
0. And if y is equal to 2x, then the probability is
P of x. P of x
P of
equal
x
to
is equal
x.
to small x. Right? So you see that these two cases are different. That means there is no single way to define this quantity in terms of individual probability distributions. And this is going to be a very, very important thing when we move further. In the future, we will see that depending on whether x is kind of related to y or not, right? In the first case, x was in some sense completely unrelated to y. We roll a first dice, then we roll a second dice. How we roll the second dice is very different from that number is nowhere related to what we got on the first dice. That's why we had a different one. In the other case, x is completely dependent on y, and then we got a different. This idea of relationship between x and y will lead to a different formula for this quantity P of x is equal to x and y. This idea of dependence and independence of x and y will be very, very important, and we will deal with it in future. For now, notice that there is no single way to define it, and that's why we need something which is called joint probability mass function. That means anytime if you are interested in a function of x and y, and you want to calculate its probability mass function, you should have access to the joint probability mass function of x comma y, which is this quantity. By definition. So if someone talks to you, oh, there is the sample space, there are two random variables, and if you want to operate on those two random variables, you should have their joint probability mass function. What are the things which a joint PMF should satisfy? Clearly, if I sum up over all possible choices, my probability should be 1. Right? And let me ask this question. What should this quantity be?
Probability of y equal to y.
Exactly. Right? For a joint probability mass function to make sense, and if you are given the individual probability mass functions, these two properties should be satisfied. This is one way to understand joint PMF. In many cases, you will only be given joint PMF which satisfies the first probability. And in that case, how can you calculate the individual PMFs? So how can you calculate P of x is equal to x?
By considering all y's.
Exactly, by looking at the second one. In some cases, all three will be given to you. Individual PMFs of x, individual PMF of y, individual joint PMF of x. Then the second condition need to be satisfied. If you are only given a joint PMF, then you can get the individual PMF using applying equation. Okay, but generally, when we want to talk about functions of two random variables, we need access to joint PMF. There is no way to get joint probability mass function from individual probability mass function. That's the thing which I wanted to highlight. Okay, so enough of operations on random variables. We saw some random variables, examples of that, functions of random variables, operate on that. But why? Why are we doing all these things? Because we said that we are interested in, some kind of operating with these numbers. And let's talk about the concept of expectation. This is one reason why random variables are so much more useful than the vanilla sample space. We can't talk about expectation if we only had simple space which had no structure. But now, since we are dealing with numbers, we can talk about expectation. What does it mean? For example, let's say there is a random experiment where there are 10 machines and the ith machine gives eye candies. You're allowed to pick, you randomly pick one machine. You don't know, which one is the ith machine. You pick one machine at random, and if it is the ith machine, then you get eye. How many candies do you expect to get?
So like,
Expectation is 5.5.
Yeah, how did you get that? This was 1 plus 2 plus 10 divided by 10. Is that correct?
Yes, sir.
Right. So you took an average, right? Okay, good. So that is the idea, right? Intuitively, that is clear. That's how you would 5.5. You would expect to get 5.5. Okay. Let's take a betting example. Whenever you have to make money, that motivates everyone. So what about if you toss a coin? Head means I will give you 1 rupees. Tail means you will give me 1. So you will lose 1 rupees. What is your expected earning?
0.
Right. This is again clear. This is the average of 1 and minus 1. Right. Tail means you gain minus 1. So you have taken the average of 1 and minus 1. But suppose the probability of head was 1 by 4. Then what is your expected earning? Would you like to take that back?
Minus half.
How did you get minus half?
We will take it like probab for head or if we get an head, then our earning would be 1, and for tail our earning would be minus 1.
Okay.
And the probability of getting a head is 1 by 4. So for a lot of data, if we have a huge amount of data, then it is the chances are that 1 by 4th of the times we would earn 1 rupees, and for other 3 by 4th times we would earn minus 1 rupees, and that would and if we add these two, our earning would be minus 1 by 2.
Very nice, very nice. So this will give you half. Another way to simplify it would be if we had done the experiment 100 times. How many times do you expect to win?
25.
25 times, right? And how many times do you expect to lose?
70.
75, right? And then I will divide it by 100 to get my earning in each of the outcomes. If I run this experiment n times, I would kind of win n by 4 times. I would lose 3n by 4 times. Again, this is expectation. I'm not saying that every random experiment is going to follow this. This is just what we expect. And then my expected earning would be half per toss. Okay, that's why I'm dividing by n, because I want to find my earning per toss, and that is half. And this is exactly what expectation is going to do. For a general random variable capital X, the expectation of X is defined to be summation over all possible X's, X multiplied by the probability that I can get X. If everything we were getting uniformly at random, this will just be an average. You can think of it as generalization of average. Right? If in an experiment, half the times you win and you get 1 rupee, half the times I lose, I get minus 1 rupees, then our expected earning is 0. But if we say that I will win 3 by 4 times, my probability of winning is 3 by 4, and then you're going to lose -1 rupees, and your probability of winning is 1 by 4, then you earned 1, then actually you are going to lose. I think I missed a minus sign everywhere. Sorry for that. Yeah. But your expectation is that you will lose 0.5 rupees in this. And if we just formalize that, we get the definition of expectation. Okay, this is the amount we expect to get if we do a random experiment. Now, the way I have introduced it and the way it is in the books, many a times people have this misconception that X will attain EX with high probability. And that's clearly not correct, right? Can you construct a random variable such that X never attains the value expectation of X?
Sir, the
previous example.
Exactly, right? If my X is equal to 1 with probability half, X is equal to -1 with probability half, what is the expectation? 0, right? And then what is the probability that X is equal to 0? So if this is not the correct concept, what is the correct idea? What does expectation indicate? What does average indicate? That might give you a hint.
Like we perform the experiment many times and we take an average of the expected values of each experiment.
If we repeat the experiment multiple times, then?
And with each experiment, we obtain a random value.
Right. So let's say first experiment I get X1, second experiment I get X2. This value will be close to expectation of X as n tends to infinity with high probability. Okay. And this is a very, very important intuition. We will formally prove these things mathematically very soon in 2 or 3 weeks. But this meaning of expectation should be clear to you. It's not that X will attain EX with high probability. That's a simple and a wrong explanation. What is expectation? If we repeat the experiment multiple times, lot of times, then with high probability, we will get something which is close to E of X. That is what we want to. Remember. Okay, and there will be, we will kind of do 10, not 10, but actually 2-3 theorems which capture this intuition. But that is for. So let's just do a few examples and then I will stop the class. Okay, so let's say you get 1 rupee if you get an odd prime on a throw of dice. What should you pay when not an odd prime? What is the probability of getting an odd prime? 2 by 4, right? Sorry, 2 by 6.
6.
Yeah, 1 by 3, right? That means I will get 1 rupee with probability 1 by 3. And if I'm paying X, this is the expected value of my this random experiment. And if I want this bet to be fair, then this expected value should be
0.
should be
0.
0. And if I want it to be in my favor, then it should be
Greater than
Greater than
Greater
0.
than 0.
greater than equal to 0.
The next has to be 0.
Then, no,
Like, if x is 0, then it will be in our favor.
no, x need, if
Hmm.
x is equal to 0, then bet will be in my favor, but x will, what do I need for x so that the bet is favorable? That's simple math, right? X is greater than
half.
X is
half.
less than
It's
half.
less than half.
X is
X
less
is
than
less than half, sorry. Right, so if I pay you 50 paisa or something, or less than 50 paisa, then I'm ready to take that bet. Otherwise, no. Notice that in these random experiments, you can't say that, okay, you want to win all the time. That's too greedy an approach. What we want is that on expectation, we will win. And now let me give you a life funda. For any game you will play in casino, the expected gain, your expected gain will always be less than. Your expected gain will always be less than
0.
0.
0. Yes.
0.
That's a good reason of why not to go to
Casinos.
Casinos,
Yes.
arcades.
Yeah. So anyway, coming back to mathematics, what should be the expectation of alpha x, or where alpha is a constant, right? What is the expectation of 2 times x, for example? You look at the formula, right? The formula was summation over x, probability x is equal to x. Right now, if I say that your expected earning is so you're at every input, if you are getting 1 rupee, you are getting 2 rupees every time, right? That's the random variable 2x. You are getting twice as much in every experiment. Then what is your expected value?
Alpha times x.
Yes.
Twice as much.
Alpha. Yeah, twice if the constant was 2 in general, alpha times expectation. This I will leave it as an exercise for you to do. Okay, not a very difficult question. Anyone wants to give me an answer? Or yeah, let's worry about. Let's give this as an exercise. I will do this fun exercise next time. Okay, we will start from next time on this examples on expectation. But yes, what we saw was we defined random variables so that we can talk about numbers associated with every outcome. And once you have numbers associated with outcome, you can add them, you can take their averages, you can take their expectation. That allows us to do a lot more math with your sample space. It will allow us to answer a lot more natural, interesting questions. And that you will see throughout this entire course. Okay, this finishes the lecture today. Are there any questions?